Well, since Apollo, hundreds of astronauts have circled the Earth in low orbit, but none has gone further. The race to the moon was an end in itself, driven by superpower rivalry. But of course, we do now depend on space in our everyday lives. GPS, weather forecasting, and communications. And robotic exploration has burgeoned. Indeed, unmanned probes to other planets beam back pictures of varied and distinctive worlds. And here's a set of pictures of Mars. Here's one taken from the surface. Here is some taken from the European orbiter. Here showing the terrain of Mars. Here's a big crater. There's another picture. And the next picture is going to show a close-up of where those two arrows are. There you are. There's a big cliff on the edge of one of the craters of Mars. And this is the Phoenix lander, which landed recently and is going to dig beneath the surface to look for evidence of water and even perhaps for life. But space probes have been still further to Jupiter to take close-up pictures of its 4 moons, the moons first discovered by Galileo. Of special interest is this one, Europa, which has ice on its surface, beneath which there is an ocean. And even more remarkable, here is Saturn, and one of the most astonishing achievements of European space science was the Huygens probe, which was launched from a spacecraft near Saturn, and it was intended to do what's shown here. It was intended to go towards Titan, Saturn's giant moon. A parachute is supposed to open, and it was supposed to land. And this was not remote controlled. It was a robot really on its own, because it takes a radio signal hours to get from here to Saturn and back. And it did exactly what it was supposed to. On the left, you see pictures taken on the way down. On the right, you see what it was like where it landed on Titan. On the left, and in the middle, it looks like you've got rivers and lakes. It's a rather attractive place. But the temperature is minus 170 degrees centigrade, and these rivers are rivers of liquid methane. So it's not a beachfront property, not an attractive place. Well, I hope that during this century, the entire solar system will be explored and mapped in detail by flotillas of tiny robotic craft. But will people follow them? The practical case for sending people into space, I think, gets ever weaker with each advance in robots and miniaturization. Indeed, as a scientist and practical man, I really see little purpose in sending people into space at all. But as a human being, I'm nonetheless an enthusiast for manned missions, to the moon, to Mars and even beyond, as a long-range adventure for at least a few humans. The next humans to walk on the moon may be Chinese. Only China seems to have the resources and the dirigist government and the willingness to undertake an Apollo-type program. But I think, looking still further ahead, expeditions to the moon and beyond will become politically feasible if they can be cut-price ventures, perhaps privately funded, spearheaded by individuals prepared to take much higher risks than NASA is prepared to impose on civilian astronauts. First people to go to Mars may go with a one-way ticket, and there will be many willing volunteers. And many will be willingly volunteered, I suspect, as well. But it will be dangerous, and there must be an overt acceptance of this. And also, we mustn't kid ourselves that going into space is the answer to the Earth's problems. Nowhere in the solar system offers an environment even as clement as the Antarctic or the top of Everest. But let's now widen our gaze beyond our solar system to other stars far beyond the reach of any probe we can now see. We've learned enough about stars to understand them, and we see places where new stars are still forming. Here in the Eagle Nebula, 7,000 light years away. There's enough dusty gas to make hundreds of new stars, new solar systems like our own. We also see stars dying. Some rather elegantly like this. This is what our sun will look like in 6 billion years. Some in a less elegant way like this. And some explosively as supernovae. This picture, which many of you will have seen before, is the expanding debris from an explosion witnessed and recorded by Chinese astronomers in the year 1054 AD. This expanding debris. And right in the middle, there is a tiny star spinning at 30 revs per second. This is a neutron star, a pulsar, one of the most amazing types of object in the universe. And I mention this because it is the kind of object where much of the research has been spearheaded by the great Job-Land telescope. And I think I couldn't be in Manchester without showing a picture of this iconic telescope, which is remarkable because it is indeed part of our heritage, almost like Stonehenge in a sense. It's really something part of our heritage. But it is also doing cutting-edge research. And I'd like to mention one of the most exciting things it's done in recent years. It's discovered that there are 2 neutron stars spinning around each other. This is an artist's impression of 2 little stars spinning around each other with a 2-hour period. And each of them has a lighthouse beam flashing towards us. And so we can study in detail the orbit of this object. And because it's orbiting so fast, only a 2-hour period compared to the 1-year period of the Earth around the Sun, the effects of Einstein's relativity are much larger. And by studying this object, it's possible to test Einstein's theory to a precision of 1 part in 100,000. And this is rather marvelous because when Rutherford built the telescope, no one had any test of Einstein's theory to better than 10%. No one knew these amazing neutron stars existed. And it's wonderful that more than 50 years later, it's been used for this wonderful fundamental science. An example of a really good investment in science. The Crab Nebula is important for other reasons, because if it wasn't for objects like this, we wouldn't be here. The reason for that was first articulated clearly by Fred Hoyle. He realized that during its lifetime, the star derives its energy by nuclear fusion. It turns hydrogen to helium, helium to carbon, carbon to oxygen, silicon and iron. And then, when it runs out of fuel, it faces a crisis, it explodes, producing debris like the Crab Nebula, and that debris contains all the kind of material that was built up in keeping the star shining. A mixture of all the chemical elements. And I don't know about the details of this, but what Fred Hoyle and others realized was that our galaxy is like a sort of ecological system, where stars are forming from pristine material, they are evolving, they're throwing the material out into interstellar space, processed into the periodic table, and then new stars form. And by this process, we can understand the relative proportions of the different elements here on Earth. Why carbon, oxygen, and iron are common, why gold and uranium are rare. So it is rather wonderful that we are part of the cosmos in a more intimate sense than you might have thought. Every atom in our bodies was made in a star which exploded like the Crab Nebula more than 4.5 billion years ago, before the Sun formed. And indeed we have within us atoms from hundreds of different stars that came from all the way across our Milky Way galaxy. We are literally the ashes of long-dead stars, or if you're less romantic, where the nuclear waste from the fuel that made those stars.